Test. Hello, Big Data Week. I'm very glad to be here to speak about one of my favorite topics. Before we get in the slides, I just want to introduce myself and EPAM. I'm a senior big data engineer. I'm part of EPAM systems for more than 2 years now, with a total of 8 years in the big data field. It looks like I generate some sort of gravity field that attracts fintech projects. I've been a daily user of Apache Spark for 7 years now. I've started with version 1.6 up to version 2.4.8. I did not get the chance to deep dive into version 3 or above due to the nature of tech stacks in fintech companies. You know how it is. Most of these companies tend to choose for paid Hadoop distributions. These Hadoop distributions have dedicated support, but they use slightly older technology versions because they're proven to be more stable. Like most of you here, I've gained my experience by days of debugging instead of hours of reading the documentation. To give a little bit of context about EPAM, we work on big-scale projects for companies in various business sectors, like healthcare, insurance, agriculture, banking, shipping, and so on. We are trying to innovate everything that we put our hands on. There are more than 55,000 employees worldwide. 10% of this number is working in the data division. In Romania, we are around 450 employees. More than 30 of us are working also in the data division. Data division is basically split into 5 categories: data science, data engineering, data analytics, data DevOps, and data architecture. Introducing our agenda for today. We are going to start our talk with a small intro of the topic. Then we're going to look at the Spark ABCs, which are a basic overview of do's and don'ts. Then we are going to look at partitioning the data, how to partition it properly, how to minimize data shuffling, and also at what file compaction is and how to do it properly. At the end, we are going to have a small quiz for everybody here through an application on your mobile phone. Top 3 people in the leaderboard will receive a goodie bag, which can be picked up from our stand right there. We'll announce the 3 winners on our display in the lunch break. Yeah, so check out our stand. Okay, why did I choose this topic? Well, over the years, I've been working and had the chance to see some very complex ETL systems and data pipelines. As you know, in the software industry, there's a big emphasis on delivering value quickly. So often engineers tend to focus on more on the functional requirements rather than the non-functional ones. It's very easy to overlook performance when the project is in an early phase. And you realize after you keep delivering feature after feature after feature that things might get slow. And what do you do then? Obviously, the first thing that comes to mind when things start getting slow is we need more compute power, we need more space, we need more RAM. Can we download more RAM? Because it's easier to blame the hardware than to start refactoring and optimizing the code. Yeah, so during this presentation, we'll look at some tips and tricks on how to use the hardware which we already have more efficiently. This way, we can save ourselves some time in the long run, and we can save some money on hardware, which will be appreciated by the company or the client. Okay, let's start with some simple tips, which most people here already know, but I cannot stress enough the importance. Step 1 on the list, stop using RDDs. Use datasets or data frames if you're more comfortable with SQL commands. Everything you do with RDDs can be done, with no doubt, with datasets. They have different APIs, yes. It will take a while to refactor them, yes, but it will be worth it in the end. Datasets, as you can see, are smaller in terms of memory due to mapping your objects to Tungsten's internal memory representation by using encoders. Project Tungsten, over here, is used in improving Spark CPU and memory efficiency. It relies on three things: off-heap memory management by using binary in-memory representation, cache locality for high cache hit rates, and whole stage code generation, aka code gen. Step 2, use caching. This goes without saying. If you're using more than one action on a data set, cache it. It's completely up to you whether you cache it exclusively in memory or you spill on disk. That's depending on how big your data set is and how many resources you have available. Step 3, make recovery easy. Nobody talks about recovery. So we have two options here. Number one, you have divided your ETL into small data pipelines, which have a short runtime and can be run independently. If you do this, good for you. You need to catch all the exceptions if they are thrown inside your code and make sure that no output data is being written. If this is done after you resolve all your issues, you can just rerun the pipeline or the batch without any issues. Number two, you have a very complex ETL system with several heavy operations on big data sets, which takes a long time to process. In this undesirable case, the architecture has already been set. You can take a checkpoint after each series of heavy operations like joins, pivots, applying user-defined functions. Checkpoints write your data set to disk and also break the lineage graph. This way, you can basically design a recovery mode when you are restarting the application. The application can check some metadata, whether it had previously failed. And if it had previously failed, it can basically resume processing from the last checkpoint. And number 4 on the list, avoid collect on large data sets. Hopefully this is visible. Collects are a very dangerous operation, as the whole data set will be brought onto the driver node, and the primary concern is that you won't have enough space in the driver process. Let's consider one scenario. We need to join two data sets, and then we need to filter out the records from a third data set. In the first case, the third data set is a very small data set. This way, we can basically filter out all the other columns and collect the IDs. Obviously, now if we collect the IDs, all the IDs are on the driver process. We need to broadcast all the IDs to the executors, and then the IDs can be used in the filter operation. This is OK if you have a small data set. In case you have the third data set is a big one, and it's obviously not collectible, you need to rethink your strategy. How do I do this? So a better solution would be just selecting the IDs from your data set, and then use a classic write exclusive join, which is basically gives you the same result as in the first case. Before starting the discussion on partitioning, let's take a brief look at the Spark infrastructure. Let's consider we have a cluster made up of 4 nodes. The driver, in this case, will be running the job in client mode, so the driver process will be outside the worker nodes. Each worker node has a hardware configuration of 64 gigs of RAM and 16 cores. To find out how we can configure efficiently the number of executors, executor cores, and executor memory in this cluster, we need to look at 3 things. Number 1, we need to set aside at least 1 core and 1 gig of RAM for Hadoop and Yarn daemons and for the operating system. Number 2, we need to stash around 7% of memory for overhead, because we use that overhead in our jobs. And number 3, use a maximum of 5 cores per executor. It has been intensely tested and proven that setting more than 5 cores per executor does not bring any performance improvement, but rather even the opposite. So if we use the 5 cores per executor, that means we'll get 3 executors per node. Dividing the 63 gigs of RAM we have left to the 3 executors will give us 21 GB. If you put aside the overhead, that leaves us with a final configuration of 3 executors, 5 executor cores, with 18 gigs of RAM per executor on each node. We need to keep in mind that one task is processed by one thread on one partition. Considering that we have the configuration I just mentioned, if you sum up all the executor cores you have available on your cluster, it will give a grand total of 65 executor cores. This number is called Spark default parallelism degree. It represents the number of concurrent tasks that can be processed in our cluster. It's important we know what this number is when tuning our partition strategy. We're going to split this discussion on partitioning based on the 3 ETL steps. We're going to start with reading the data, with extraction of the data. Using Spark, we have the ability to read data from various sources, basically files from distributed file systems, relational databases, NoSQL databases, streams, or even queues. Due to the limited amount of time I have on stage, I'm going to focus on the first 2, distributed file systems and relational database. Say we read some files like CSV, Parquet, JSON, ORC from HDFS into a dataset or data frame. How do you know how many partitions you are going to have? It's important you know this number, especially if your operations won't include any data shuffling and further processing. So when reading the files using the dataset or data frame API, there are 3 variables used to determine the number of dataset partitions. Number 1, Spark SQL files max partition bytes. This variable specifies the maximum bytes your partition you can pack in a single partition. Number 2, Spark SQL files open constant bytes. This is an overhead per file, which is used in some calculation. And number 3, Spark default parallelism degree, which I talked about earlier. The file maximum split size is a min function between the max partition bytes and bytes per core. Bytes per core is calculated as the sum of all data files plus the number of files multiplied with the open constant bytes. That's the overhead. We take all this and divide it by max partition bytes. Let's say we are reading just 2 Parquet files, 450 megabytes each. After we make the calculation for bytes per core using these 2 files, we will get bytes per core equals approximately 12 megabytes. So obviously, the max split size will be 12 megabytes. If we're splitting a 450 megabyte file into 12 megabyte chunks, that gives us 38 partitions per file and a grand total of 76 partitions. Obviously, if we would have read a much more bigger volume of data, like gigs, tens of gigs, then max partition bytes would have taken precedence, and we could tune the number of partitions by using that variable and tune it however we like. That's the key takeaway from this slide. When reading datasets from a relational database, we have a lot more control over partitioning. Using the data frame reader, we can specify exactly the number of partitions we want our dataset to have. Depending on the dataset size, rule of the thumb is you should probably use a multiplier of the Spark default parallelism. In this case, I've set 150 partitions, which is 2 times the Spark default parallelism. Also, we can specify a partition column, a lower and upper bound, and these generate queries dynamically for each partition with creating a unique where clause, like in that query example. Formula is right here. Additionally, there is some other tuning which you can do on the database side in order to improve reading speed. First of all, you need to tune how many concurrent connections your database supports and make sure it can accommodate that. Number 2, you should probably create a partition column. As an example from Oracle database, I use the Nora hash function on several columns. That's to increase string uniqueness and have better data distribution. Upper and the Aura hash function has, besides the column to hash, we have the upper bound, the max bucket size, which should be the same as the upper bound, 449, and the seed value of your choice. Another tip is that you can use composite partitioning on your table. You can use hash list or range list so that each Spark partition will read multiple database subpartitions. As you saw on the previous slide, using the data frame reader, we can only read one table at a time. But if we have a very potent database, Oracle Exadata, for example, we may want to put those indexes, material views, and Oracle functions to work. And we can put some of the initial joins directly in the query. We can do this by using a Spark range, defining exactly the number of partitions we want in our range. And for each partitions, we can have then other functions which open a JDBC connection to our database, and we can customize ourselves the query with the where clause on the partition column. Given that I put 450 partitions here, and the step is 1, in the sample query, we can also use the partition ID from task context. It's very easy to get it. Otherwise, you should use the integer from the Spark range in the query, in the where clause. Data shuffling, every data engineer's arch nemesis. The truth is that shuffling is actually beneficial. For example, in large dataset joins, large dataset joins could not be done without shuffling. Dataset shuffling is triggered mainly by 3 transformations. That's repartition, joins, and aggregation. They're also called wide transformations. Regardless of how many dataset partitions you have, once shuffling occurs, the number of partitions in the resulted dataset will always be Spark SQL shuffle partitions, which is 200 by default. This parameter can be tuned however you please. I suggest you can do some testing with maybe a multiplier by default partitions and see which suits your data volume better. Avoiding shuffling in datasets can be done only if one of the datasets is smaller, and it's called broadcast join. In this case, you basically broadcast the small table to all the other executors, send a copy, and all the other partitions can use that data, so you don't have any data shuffling. In Spark version 2 and above, you have a variable called Spark SQL auto broadcast join threshold. This is set by default to 10 megabytes. That means a dataset will be automatically broadcasted if it's smaller than 10 megabytes, even if you don't do it explicitly by yourself. I would recommend to disable this variable, set it as -1, and take full responsibility for all your broadcasts. I also wanted to talk about how to optimize large dataset joins, but we don't have enough time allocated. So if you want to chat about it, you can join us at our stand. Last topic is about file compaction. It's quite important for space and query efficiency. If you write your resulting dataset or data frame into files, then the most important tip is don't coalesce your data to write fewer files. Coalescing means shuffling your data, means longer process time, and the biggest downside is that you may not have enough memory on your executor when you are reducing the partitions. On the other side, the clear advantage is less time to data for your clients. If HDFS is your output system of choice, let's talk about why small files are harmful and why I just recommended you to do that. Files in HDFS are broken into block-sized chunks called data blocks. Starting with Spark version 2, this data block is 128 megabytes by default. I'm sorry to disappoint you, gentlemen, but bigger is better. Luckily, I'm talking about file size here. So, the issue here is that a 10 kilobyte file will take the whole data block the same as a 100 megabyte file. So basically, small files will waste your whole block, not to mention the time it takes to read thousands of small files versus tens of big ones. If your batch process reads different volumes of data daily, weekly, then your input data will vary. Sometimes your data set will be small, sometimes your data set will be big. So that's why I recommend creating a custom compactor in the end. Here's another tip you need to keep in mind. File size in memory is different than file size on disk. For example, CSV files are smaller in memory, but are bigger on disk. Parquet files, on the other hand, due to how data is stored inside them, are bigger in memory, but are smaller on disk. So there's no way to accurately get the size of the data on disk. Actually, you just written it out. As a result, we have to write the files twice. That's why I recommended to write the files as they are in the first place. The compactor processing logic should be fairly simple. Given this scenario, we just need to get the file sizes from the temporary path. Yeah, we can do this by using like a file utility library. Then you need to get the block size and just use a ceiling function to get the number of partitions. Then obviously you can read all the files in the temporary path, repartition to that number of partitions, and write them in a final location. I want to finish with this last slide regarding data availability. If you have some tables created on top of your files, that means you have downstream consumers which are eager to read the data. To minimize time to data as much as possible, there are several approaches to do that. I'm going to name just two right here. First of all, you should consider creating tables on top of the temporary files you just wrote, and also create tables on top of your final files. Then create a view, which is basically a union of this table, and tell your clients to use that view. The problem here is there is still a very small window between the time you write your final output files and the time you delete the temporary ones. If you are using Impala to read that view, then you also need to refresh all those tables. That takes additional time. So if your downstream consumers are very picky and require millisecond precision, then you can basically put some logic inside your compactor, which will update like a metadata table. And once the compaction finishes, it can set the flag like is live equals true. And you can use that flag in your query, in your view definition, by joining to the metadata table. Obviously, this has a small downside as well, because there is an extra join in the view. But if we keep that table small, and maybe use HBase or Kudu, or there shouldn't be any issues. Okay, that sums it up. It's time to play our little quiz, like I mentioned. The first 3 people who will answer correctly will win a goodie bag. I'm going to ask you to access menti.com and use the user code provided here. Please use your first name and last name when accessing the quiz. And I'm going to ask you to take a screenshot of your phone once the quiz is over. This is kind of a 2-factor security system to prevent cheating. We had some cases in the past. Waiting for thumbs up. You will have 30 seconds to answer the question, 15 seconds to read the question, and 15 seconds to answer it. First question: which transformation returns a new discretized stream by selecting only those records of the source discretized stream for which the function returns true? Okay, time's up. Obviously, the answer was B. Second question: select the option which is not the cluster manager for Apache Spark, standalone version, Yarn, Apache Mipos, Kubernetes. Okay. Should be an easy one. Obviously, it was a trick question. There is no thing as Apache Mipos. Moving on. What should you do when you should avoid doing when you manage large amounts of data? Counting, collecting, or joining? Question was collecting. We just talked about this. Hope you didn't answer different. Are user-defined functions optimized by the Catalyst optimizer in Spark? I didn't talk about this, but I hope you guys know the answer. Maybe it's an option too. Could be the right one, but it's not. Okay, I want to thank you for your attention. You've been an amazing audience, and if you leave this session with at least few ideas on how to optimize and improve your current data pipelines and batch processes, then my mission here is done. Are there any questions? No Spark users here? Come on, don't be shy.
Maybe if there are no Spark users so far, how would you convince somebody that's not using Spark to cross over?
To cross over to using Spark?
Yes.
Obviously, this is the decision that data architects must take. Yeah, if we have large amounts of data, you could consider using some sort of serverless, maybe other serverless functions. If you have your data in the cloud, you can also have, we have Cloudera here. You also have solutions from Cloudera. They have clusters in AWS. You can use that. If you have large amounts of data, I think from my point of view, you should be using Spark if you have heavy operations on it. There are alternatives like Apache Flink. You have options for streaming, although maybe I'd recommend Apache Flink in streaming rather than Spark streaming, which has micro batches. But with the latest updates of Apache Spark, starting with version 3, I strongly recommend you look into that. There are many advantages and many improved functions, and it improves memory optimization and how quickly it processes your data even more.
Honestly, Gabriel, my team is not using Apache for now, but after your presentation, we just might really seriously consider it.
I hope so.
Thank you very much.